Hey everyone, this is the SensrLink group. Here we're going to be showcasing our demo video. In the first part of our video, we want to go over the sensor pre-calibration stage. As a current demo, we are going to be using a breadboard circuit, which includes our variable gain and offset amplifier, an Arduino Uno, which will be used to digitally tune and calibrate the gain and offset, and then we'll be having this analog discovery as acting as our oscilloscope and wavegen. In this figure, we can see a plot in yellow and a plot in blue. The plot in yellow is a probe measuring the wavegen's sinusoidal input signal prior to the calibration, and then the blue plot is showing after using some amplification and adding in offsets. The main reason we have this is so that we can adjust the analog input signal such that it's operating in a proper region to be able to feed into the ADC for the next stage. The way this works is we have the Arduino be able to program the gain and the offset. So if we adjust the parameter for the gain and increase the offset, we'll see that after we update it in just a minute, that now the blue plot has an increased gain and also an increased offset. And we can see that now it's operating between 2 and 4 volts approximately, which is a better operating region for our ADC, which ideally accepts inputs between 0 and 5 volts. The next part we'll be going over in more detail of how this gain and offset amplifier can easily tune for the sensor.
In this part of the video demo, we will be going over how the variable gain and offset amplifier works. Shown below is the schematic of our variable gain and offset amplifier. Notice we have two resistors, R1 and R2. These are digital potentiometers that are controlled by the Arduino Uno to change and tune to our liking. In this case, R1 adjusts the offset while R2 adjusts the gain. Shown on the plot on the left is an example of what our output looks in relation to our input. Shown here in blue is the input signal plot, which is a 400 millivolt peak-to-peak waveform. Shown in orange is our output signal. You can see in the left region in the red box that we are able to adjust the offset by adjusting the potentiometer value R1. Later on in the green box, we can see that we can also tune the gain using potentiometer R2. As an example, here's a video of what the waveform would look with relation to time. We can see that we are able to adjust the offset up and then down. Next, we can also adjust the gain, again up and down. That concludes the variable gain and offset portion of the video demo.
Okay, now that we've addressed how we plan to adjust and calibrate the analog sensor signal, we can now go into moving on to describing how our full ADC works. In the video here, you can see the voltage controlled oscillator, which is designed on a PCB. It has 11 outputs, which we are going to be connecting to our FPGA, shown over here. This FPGA is already programmed to have the full digital output in the design. And then lastly, we have 16 pins over here, which are then connected into our Discovery 2 again, but this time we're going to be using the logic analyzer to actually read out the digital output for the system. We also have a power supply that will be supplying our VCO circuit with the 8 volt VDD supply voltage, and this is just so that we can actually power our circuits. And on my computer over here, we have the setup for how we're going to be measuring this data. So this is the logic analyzer, which is going to be measuring 16 pins as our digital output. We also have an oscilloscope, which we probed to the sensor's analog input signal. This will be so that we can actually compare what the input signal is compared to the digital output. For the first demo, we'll be just starting with a really slow sweep, ramp-up sweep between 0 and 5 volts. So when I run this, and then turn on the logic analyzer, we can now see that as the ramp function increases in voltage, we see that the digital output is gradually increasing. Right when we hit 5 volts, we'll see that it will drop back to the lowest point. See? Yeah, right there. It went up from around 600 digital output peak, and then to swap back down to the lowest digital voltage, or sorry, digital output. And again, we'll be able to see it happen one more time, just to verify. So that's good. Now for the second demo, since we want to also be able to verify that this works at higher frequencies instead of just a slow DC ramp up, I'll be adjusting the signal so that it will be, let's say, a 100 hertz sine wave as our analog input signal. Now when I run this, you can see on the right is the sinusoidal wave. And we can see that this digital output is running a lot faster. It's very difficult to actually see what's happening. If I slowly zoom out on this, it starts to become a little bit more apparent what's happening. I'm going to zoom out just one more time. Alright, I'll just pause, do a quick pause. Now you can kind of see, like visually, how the digital output is actually mapping out a sine wave function. Where we see over here is the part where we have the highest digital output, and these minimum points is where we're seeing the minimum digital output, which is near the 0 volts at the bottom of the sine wave. And then if we zoom in even closer, you can see the actual individual digital outputs for each of these instances. In this case, we see that the digital output is sampling the analog input signal at a frequency of about 10 kilohertz. Actually 10 kilohertz exactly. So that's the rate that our ADC is currently sampling the analog input signal from our sensor. And in essence, that's how our full VCO ADC design works. And after this, all I have to do is use my file and then export this data, and then be able to do the last lookup table correction and signal processing on MATLAB.
We are using a lookup table based correction which maps known incorrect output values to its corresponding analog input value. This relationship is then generalized, and we use it for other waveforms. Shown here in the plot on the left is the lookup table based correction, and how we are mapping our known incorrect output value, shown here in blue, to its corresponding correct analog input value, shown here in orange. Shown here is an example of the output of our ADC before any lookup table based correction. Shown in orange is the ideal 100 Hz sine input, while shown here in blue is the output of our ADC. We can see that it's a close approximation, but it's not quite correct. Furthermore, we can actually see that our system takes the discrete steps to approximate the known input. Now, after we put it into the lookup table, we can see that we can correct some of the nonlinearities, particularly in the bottom portion of the waveform. We can see that it kind of stretches out a bit and more closely approaches that of the input. We still see the discrete steps, but that's intended as it is a digital output. We can better see the results of the lookup table based correction when we compare the spectrum of the before and after. Here is the spectrum of the digital output before lookup table correction. We can see that we have the fundamental frequency of 100 Hz, but we also have the second, third, and fourth harmonic present. When we compare this to the spectrum after the lookup table, we can see that we got rid of some of the second, third, and fourth harmonics, but we still retain some of the fundamental. That is how we are able to correct for any nonlinearities and distortion in our system.